Welcome to today's Bible study seminar. Today we are extremely delighted to have Mr. Santosh Vempala again. Santosh graduated from CMU in '97 under the supporting Adam Blum. He was an associate professor at MIT before he moved to Georgia Tech, where he is currently the Frederick Story Chair and a distinguished professor in computer science. His research interests broadly span algorithms, geometry, randomness, in particular algorithmic tools for sampling, learning, optimization, and data analysis, high-dimensional geometry, randomized linear algebra. And more recently, he has also been studying theoretical models of computation by the brain. Santosh has received numerous awards. He is a Miller Fellowship. He was named Fellow of ACM in 2015, and in 2022 he was named a Fellow of American Mathematical Society. He was also the founding director of the Algorithms and Randomness Center at Georgia Tech. For a joint work with Richard Peng, Santosh has received the Best Paper Award at SODA 2021 for his work on solving sparse linear systems faster than matrix multiplication. And throughout his illustrious career, Santosh has advised a cohort of brilliant science when I am personally working with my previous Vempala and close collaborator Santosh Pandey. So yeah, welcome Santosh.
Thank you. Thank you. I'm only going to use the board, so please let me know about the font size and you want to come closer. So the talk is about a learning theory problem. And it's partly motivated by the brain, but you'll see it's very much formulated like a machine learning theoretical problem. And please ask questions. Maybe some of what I say is already familiar. We can move on to things. I hope to show you most of the proof, but we'll see. So the setting is the following. Typically, at least in the traditional style machine learning, we would get one problem, say a classification problem. You get labeled examples, and you want to figure out the rule or a rule that approximates the correct labels with not too many samples and efficiently, not too much time. So you get one task. So for example, the task might be that you're getting points in space, and each point comes with a label. I mean, the label might be just 0 or 1, or it might be a real number or something else. And you get a series of these. And then eventually, after seeing some number of examples, you want to come up with a rule, with an algorithm, so that if you give me a new x, you can apply your approximate version of this labeling function. And the point is, you want to say that your output is close, or is the same as the true output most of the time. Right? So you measure this either with the probability of disagreement, if it's a class labeling problem, or with some kind of loss function, if it's a continuous variable. So that's one problem at a time. But the way, let's say, if you could, one high-level thing that we seem to do is learn over time, not from one task, but sort of you might figure out how to walk and how to eat something, and you keep applying this knowledge about the world to learn new tasks, and things become easier and easier, and so, or even within math, if you know how to multiply and take logarithms, and things become, you start using those facts. So the question is how to model this idea that you are able to learn things more efficiently because of what you've learned in the past. Okay. So the first setting of the problem is that we have a sequence of tasks, not just one task, sequence of tasks. And the way we'll model it is either we just think of it as different labeling functions coming one at a time. So maybe one labeling function is to figure out chairs, and then it's to figure out tables, and then it's to figure out buildings, whatever it is, right? And so on. And so the point is, if you've already learned to do chairs and tables, and then is it easier for you to do something else? Okay. Right. So I had a notebook, didn't I? That's it. Okay. Yeah, I don't need to. But, okay. So let's see. So this is we have a series of, let's say, m tasks. M tasks. Okay. Each task comes with label examples. It's an arbitrary, the order of these is arbitrary, but they come with label examples. So each task has a set of points and a labeling function for it. Okay. So we'll just call the labels y. So you get a bunch of pairs like this for task 1, then task 2, and so on. Okay. Now, typically, and also in the first formulation of the problem, this is the pack model, we think of the x's, the points in space, as being drawn from some distribution. Okay. But even the distribution could be different for each task. First task distribution D1, they're all drawn. Second task, they're all drawn from some distribution D2, and so on. So the different distribution examples, you know, if you think of the distribution as distributions on, I don't know, pixels or wavelengths, or, you know, frequencies of what you see, of course, the distribution could be very different for furniture versus apples versus animals. Still, there, you know, knowledge of the physical world might what you learned in the past could still be useful. Right? So distributions could be different, labeling functions could be different, and so this is the distance. That's the input. The goal is to learn a classifier for each task that has smaller. So in addition to all this, you're also given a target epsilon greater than 0, and you want to learn every task so that with high probability, your error on the same distribution for each task, meaning for this task I on distribution I, your error should be less than epsilon. The largest error should be less than epsilon. That's your goal. Okay. Error less than epsilon on all tasks. Now we could do this with the regression type problems or loss functions and so on, but let's, for this talk, stick to just 0-1 labeling functions. Okay, is it the object? Is it this type of object or not? Does it belong to this class or not? So the yi's are going to be just 0-1. Okay. Okay. And by the way, these are different tasks. Another common setting in machine learning is where you have lots of classes within the types of labels. So, for example, there is ImageNet 1000. There are many different kinds of objects. Each type of object is a class. And so the lifelong learning problem there is you learn some tasks, some classes, and then you learn a new class, and a new class, and a new class, or a batch of 10 new classes, 10 new classes, 10 new classes over time. And you'd expect that because these are all somehow objects from the physical world, you know, after you learn some, it gets easier to learn the remaining part. You shouldn't need as many examples for as much time. So that's the class incremental learning. It's a similar setting. You can think of it as learning a classifier for each class, for each label class. So instead of tasks, it will be classes. Okay. So that's the goal. Now, yeah. So how should we do this? I'm going to consider two settings for this type. Of course, to make any progress, even for a single task, we have to make some assumption on what is the type of labeling function. If I tell you nothing about the labeling function, of course, the labeling function is random. There's no chance. The next example's label, you have no. The previous examples don't help you at all. Right? So you have to consider some class of hypotheses. One common important class is the linear threshold functions. So we say for each task I has a vector, right? So sort of a target vector. I say. Okay. And the label, so the y is just the sign, right, of the inner product of the example. So take the inner product of this target vector in the example, and so it's +1 or -1. I could call this -1 +1. So it's a sign. So this is a linear threshold function. Right? So there is some linear function given by a vector AI, and it could be, these are pluses here, minuses here, depending on the size. So each class is its own classifier, right? So it's like some linear combination of the features of the input. If it's above threshold, it's 1, otherwise it's -1. That's one setting. Another setting is that these features, in this setting, the features are just the original input features. You take a linear combination of them. Instead, you could have nonlinear features. So we first have a set of nonlinear features, some sigma 1 of x up to some, these are now real numbers, up to some sigma, let's say, L of x. And each label, the labeling function, is the sign of some linear combination of the labels. I mean, of the nonlinear features. So this is like a, and I said just nonlinear features. So this could really be some network sitting there. Doesn't matter. Somehow it has generated these features. But at the end of the day, we're taking the classifier to decide whether it's one of them. So it could be more general. You don't have to. In this case, the sigma 1 is just x1. It's just identity, picking out the ith coordinate. Okay, these are the two settings to consider. Now, this problem, note that even for one task, it's hard in general. You have to make assumptions. Getting that. This problem for one task is fully solved, meaning for arbitrary distribution D and any target error epsilon. So the classical theorem says that linear threshold classifier can be learned to within any given error epsilon greater than or equal to 0 using order of d over epsilon log 1 over epsilon 1 over epsilon log 1 over delta samples, labeled samples, right, in polynomial time. These are, what is D? D is the input dimension. So each x is sitting in RD, and each example is given to us in RD. And epsilon is the target. Delta, this is with probability. The whole thing happens with probability 1 minus delta, at least 1 minus. Okay. You need that because these are random sample from distribution. You could get really unlucky and you get only something in small areas you have no idea. But it's only logarithmic dependence on that. But this is a general theorem. In fact, this doesn't apply. The polytime part is important. It's important that it's half spaces. If you want to talk about sample complexity, that's a much better understood question. We can replace this D here with the VC dimension or other measures of the complexity of the class. In the case of half spaces, it's just linear in the dimension. Okay, so that's one example. For one sample, it's a set here. In the rest of the talk, I'm going to sort of ignore this factor because we always have this and focus on. I mean, we'll always have this. I won't write it. Okay. I mean, one way we can write this whole thing is O tilde D over epsilon. So ignoring logarithmic factors. Okay, so that's one class. Now, if I apply this naively to m tasks, like in this case, right? There are m classifiers of P1. Then let's see, what's the sample complexity going to be? Right? Just you see the first task, apply this algorithm, learn it. And by the way, this is one way to do it is just use the linear program to find any feasible solution to this many examples that will already work. So task 1, you get error epsilon, task 2, you get error epsilon, so on, keep doing that. What would be the total sample complexity? Is it okay to make the talk a little interactive? Even though there's, right? There are m tasks total. Right? Basically, I'm giving you a multiplication problem. Right? What's the answer? Yeah. Yeah, sample complexity. Yeah, m is the number of tasks. Each one takes d over epsilon. Yeah, m times d over epsilon, right? Up to log factor. Okay. Think of m as super huge. D is also huge. I mean, these feature dimensions are big. So this is very large, right? Yes. Yeah, but that's the goal, right? Each task has its own. So you can't use the separator for apples to learn chairs, right? Each one has a different task. So this would be the naive thing. And in general, with no further assumption on the task structure, you can't do better than that. Right? Knowing solving the first k tasks, you don't know anything about the next task. Could be any classifier out there, right? Okay. So what can we hope to do? How can we try to? How could past knowledge be useful? There must be some common structure in the tasks. At a high level, there has to be something common. The question is what? Right? We have to make some assumption on what the common structure is, and then we can make progress. So the assumption that we'll make here is that. Oh, I was about to pull down a bolt, but this is the. I guess there's an extension there. Okay, the assumption we'll make for the common structure is that all of the classifiers, the true target classifiers that exist, A1 through AM, right? M of them, they all lie in a k-dimensional subspace, which is much smaller than the dimension D. Of course, they all lie in D dimensions, because the whole problem is in D dimensions. But suppose they have D-dimensional vectors, but they have a common subspace. Okay, so let's understand this assumption a little bit. Oh, right. That moves, right? Yeah. I'll leave some. Oh, it might be terrible for the yeah, indeed. Okay. Yeah, in-person bonus material. Only figures on this board. So so there are these vectors A1, A2. That's already a two-dimensional subspace. In general, if I start having up to D, it will become a D-dimensional space, right? You grow proportional number of vectors. But we are assuming that there is a low-dimensional subspace, say k-dimensional, and all of them, whatever is the number, they all fit here. Okay, so in other words, there exist k features, right? Unknown features, vectors in space, so that all of your classifiers are linear combinations of those k features. That's the assumption, right? So there exists. So all of your target tasks lie in a k or close to it. Let's just say lie in it, but it won't matter if they're close to it. That's the assumption. All classifiers lie in a k-dimensional subspace, where k is much smaller than k. Now can we do better? First, let's see sample complexity, which means your algorithm can take exponential time. If you allow yourself only sample complexity, what would we do? Okay. Before we do that, I just mentioned most of the talk will focus on this, so I can give you details, the linear case, but a lot of what I'm going to say is going to apply to the nonlinear case, especially the sample complexity. And so in the nonlinear case, the assumption we'll make, same thing. There is the original input vector. Then there are these nonlinear features, right? So these are not just vectors, it's just linear combinations. Rather, each of them has some nonlinear state, let's say like a balloon, whatever. And so, but they're only k of these. This is the input dimension. This would be huge, D. Then there are k features here. Okay? And then on top of this, there are classifiers. These are M of them, which are only combinations of k nonlinear features. The point is that that's the common structure. Only k nonlinear features. Even though the input dimension is D, the number of tasks is huge, and there is a common shared structure. So if we allow ourselves this assumption that there are k features, what all the features are in a k-dimensional subspace, what can we hope to in terms of the sample context? Go back to the interactive part of it. Any guesses? Well, that can't quite be true, right? Imagine m is 1. If m is 1, you have to get d over epsilon.
After k classifiers, you actually know k vectors in that subspace. But you get k independent vectors in the and you can
Good. So if you know the subspace, if somebody tells you the subspace up front, somehow you figure out the subspace, then from then on you won't waste your time looking at all space. You just work in that subspace. You'll project all your points to that subspace and find your classifiers in that subspace. That subspace is dimension only k. So from that point onwards, it will take you whatever is the number of tasks left times k over epsilon. Right. So there's an mk over epsilon. Great. Well, what about the time to get down to this k subspace? Right? How many samples do you need for that? Now, if you were to find this exactly, the AIs, and they were linearly independent, sure, then you would have it. But we're finding each one to some error epsilon. Nevertheless, how many distinct subspaces are there that are k-dimensional? We can count this using this dimension. When to specify one subspace, you need k vectors. Okay. So, and each vector is d-dimensional. So basically, the number the sample complexity is this. So you need d over epsilon times k plus m over epsilon. So instead of d times m, it's d plus m times k over epsilon. That's what it does, right? D plus m over epsilon times k. But this is just sample. What's the algorithm? Right? We need an efficient way to do this. So yeah, okay. That's the sort of algorithmic question in lifelong learning. How do you algorithmically achieve from our assumption of common structure, we get a lower sample complexity bound, and now we want an algorithm. And the algorithm should be on the fly. As you see the next step, you shouldn't have to wait for a certain number of tasks and then you put it all into one learner. Yeah. Okay. So what is the so Ayush, right? You suggested the algorithm of you learn the first classifier. Say you call it A1 tilde. Okay. And it's close to the correct one. Right? Now remember that already takes some work. Why should the fact that it has small error mean that it's close to the subspace? Because the first task, maybe there's lots of options. Right? The data happens to be separated. Right? So all of these planes will work fine. Anything in this plane will work fine. But to get the target subspace, you better pick a particular one because of the other ones that will come up later. Right? So that could be a problem. Just the fact that you have low error does not mean that you have small distance between what you find and the target. So one assumption that we'll end up making actually is the assumption that in the data, that's the only assumption actually we'll make. If you have low error, you are close to the target. Okay, and this is satisfied by lots of distributions. For example, all log concave distributions. Basically, when you have the distribution, you shouldn't have large gaps in that. That's the assumption. There shouldn't be large parts of space with no density. That's what you do. You need something much weaker than log concave, but what we want to say is low error in the low classification error implies small distance. Okay. So you found A1 tilde, that's close to some A1, right? Great. Now comes A2. Maybe let's say the true, okay, I'll try to draw this. This is the true subspace with obviously two-dimensional here. Now, A1 is a little bit off, right? It's a little bit off from A1 tilde. Now now you want to learn A2. Now, suppose A2 happens to be quite close to A1. It's on the same subspace, obviously, but it happens to be quite close to A1. Not the same, but close. Now, I'll give you some approximation to A2, which is within epsilon. Now, the problem is that even if you learn A2 very well, look at the span. Let's say A2 tilde equals A2. You learn it perfectly. Look at the span of these. These two vectors give you a very different span from this one. So, again, even though the angle between A1 and A1 tilde is small, and A2 and A2 tilde is 0, the angle between the corresponding subspaces can be huge. Because that angle is a little lemma, right? Depends on the ratio of these distances. Okay. So in particular, the sine of the angle, by theta I mean the angle between, let's say, the span, I'll call it V tilde, and V, can be as large as the sine of the angle between the vector you just added, say, one of the A's, A1 tilde and A1, divided by the angle between the A1 and A2. Can be as large as this. Right, I mean, is my picture clear? Let me try again. This is one vector. Now what I want to say is, suppose I have, these vectors form my subspace. These are A1 and A2. Okay. And I have to draw somehow this subspace. Okay. Now, or maybe I should draw it. Yeah. Draw it more like an ellipse. That's the subspace, right? Now, I will learn one of them to some error. Say up this measure. No, oh, I see this. Yeah, I know how to draw this out. Okay. This is A1 and A2. And that's the subspace. Now I learn this one to some error. It's over here, A1 tilde. Right? Now look at the span of A2 and A1 tilde, right? And those, that means it goes through these two. This will be something like that. Right? So the angle for the worst points, which is how you measure the angle between subspaces, the maximum angle between unit vectors, the unit vector and its closest vector in the other subspace, will depend on this here divided by this here. That's all we say. That's all we say. Okay? So this is a problem. How should we overcome this? So let's try the algorithm again. So you suppose you have already learned A1 tilde up to some AL tilde. And you get the next task. Okay. And first thing you try is, don't try to learn it in full space. Try to learn it in the space that you have so far. So this is V tilde, right? Learn A in span, A tilde in the span of, this is the next task, AL plus 1 tilde, only in V tilde. Meaning, you're only trying to find a vector in this span. So then the sample complexity is not high because this is low dimensional, you know the space. So you would have only used L over epsilon examples to try this, if you want to target L over epsilon. Now, yeah, let me call it different parameters, but you try to learn it with a small number of examples. Now, if the error is small, if error of a tilde L plus 1 is smaller than your target epsilon, then you're happy. Don't add any more features. That's it. You don't need to do anything else. You want target error epsilon, you want it. Else, if the error is larger than some target, then what should you do? Huh? Then you learn a new feature and you spend your D over epsilon. Else, learn more accurately, right? A tilde L plus 1 using more features, right? More examples. Learn, let's say, to error. Instead of epsilon, I'll call it epsilon prime. So you might need to learn it more accurately than the overall target. So we'll give ourselves that feedback. That's it. This is the plan. You check whether a tilde has small error if you restrict to what you already know. Otherwise, you learn a new feature. It's kind of like what we do, right? You learn some things initially, depending on your field or whatever. And then when you learn a new thing, you first try to map it sort of to what you already know. And if it's far, you might decide not to learn it, or you might have to sit down and learn it. Then you add to your toolbox or whatever. Right? I mean, it's the same with not necessarily math. It could be something we do in life, like how to eat something. Okay. So okay. So this is sort of the simple lifelong learning algorithm. I'll call it LLM, lifelong learning. Okay. What kind of guarantee can we hope to give here? So the theorem for this is that assuming that all the distributions satisfy the data assumption. Remember, this means that the probability of error is approximately the distance to target. The Euclidean distance to target, right? This is the assumption. Under A1, right? This was in 2015, joint work with Balkan and Blum. Under A1, this algorithm, LLL, learns and tasks to error less than epsilon using order of, or tilde, let's say, of dk squared over epsilon squared plus mk minus. That means. And in polygon. Okay, so that's the thing there. But even this is sort of maybe not completely obvious, right? Because as we saw, we have this issue. So the problem is this. This comes down to a nice question, just a pure question about approximation. I have two subspaces, say U and V. U is the span of vectors, say U1 up to UK. And V is the span of vectors V1 up to Vk. And they're all closed. I mean, for each UI minus each EI, they're all unit vectors, first of all. Everything is a unit vector. And these distances are less than epsilon. Right? So for k vectors, we have found within epsilon. So now the question is, how far are these distances? We already saw it can be arbitrarily far. So we have an additional assumption, which is that in one of them, the next vector is far from the span of the previous ones. So like this. So what we're doing here is that if it's far, then you learn it, right? So we want to say that the next vector A2 is not very close to the span of the previous ones. So the assumption is that Vi plus 1, let's say sine of the theta angle between this and the up to I. So I'll call the capital Vi, span of the first I. The angle of the next one with the span of the first I is at least some gamma. So every time you add a new one, it's at least gamma away. and then everybody. And meanwhile, this one is close to some target. And now the question is, under this, can we say something about how close is U? So the main lemma there was that under these assumptions, the maximum angle, which we'll call theta between the subspaces U and V, is bounded by basically order of k times epsilon over gamma. For gamma sufficiently small, gamma has to be something like epsilon squared over k, or k squared. Yeah. So for gamma sufficiently small, and no, not for gamma, sorry. I don't need to say anything more. That's. So the point is that if you have k vectors that you're finding close approximations to, the overall error can go as k epsilon over gamma. So what we do is, when we learn a new feature, we set the target epsilon prime to be epsilon squared over k. That way, when you plug in this here, you still, and gamma is still epsilon. So to make this, let's say we're learning up at epsilon prime, right? That's what we're actually doing. And so then this will be epsilon prime. Now if I set gamma equals epsilon, and epsilon prime is epsilon squared over k, this becomes order of k squared, order of epsilon, right? Which is what we want. Meanwhile, though, the running time depends on dk over epsilon. I mean, the overall error, remember, is we have to learn d over epsilon prime per feature, and we have to learn k such features, which if you put in that now, you get the dk squared over. So this is just a quick overview of how this bound works. So this is an extremely simple algorithm. You just add new features, but you only add them if what you already know is not good enough. You have to choose your thresholds a little bit carefully. That gives you this. This seems to be the best trade-off. Seemed to be. Okay. So natural question here now is, can we do better? Right? Remember that the VC dimension bound suggests not this part is correct. This one should be dk over epsilon, not dk squared over epsilon squared. Right? Because it's only k features, and it should be. Why are you spending this extra energy? Okay. So, how could we possibly improve the algorithm or the analysis? That's the question. Any suggestions are welcome. Thoughts. Right. So one thing we're not doing is ever refining what we already know. Right. So I think a good thing to do is when you realize, oh, what I thought was not quite right. Let me change my view a little bit. It will make it easier to absorb the world. So this is not necessarily what everybody will do, but it's a better algorithm in this time. Okay. Great. So how should we define it? Right. So we're going to add a twist to this algorithm. Simple, small twist. Every once in a while, right? Maybe on your birthday or something, you will look at what you already know. Decide, oh, those are not the best features. I'm going to view it slightly differently. Okay. Make an adjustment to that. When you make the adjustment, you want to make sure your error and everything you've learned so far is still small, right? But somehow you want to improve it. So what's the goal there? So we'll call this representation refinement. Okay. So you've learned a bunch of tasks, and let's say you've learned A1 tilde to sum AL tilde. That's all you know. You don't know the truth, of course. This is all you have in your head. That's what you know. So you want to find a subspace. Find subspace V, right? Such that distance between AI tilde and B is less than your epsilon or epsilon prime, whatever you want to keep it at. Fine. But in addition to that, I want to minimize the dimension of V. Find me the smallest subspace that achieves this error bound. A trivial solution without this is take the span of these. That's what we're doing right now. Right, but this is going to keep growing. It will grow all the way up to k squared. But now we're saying we know that there is a k-dimensional subspace. So every time you have this problem, there is a solution which is only k-dimensional. So every once in a while, let's adjust the subspace and make it low dimensional again. Now, of course, this is a hard problem. Minimizing rank, minimizing dimension, subject to these constraints. Even though the constraint is convex, it's just saying these are points given to you, and you can try to represent subspace by matrix. In this, it seems hard. So let me relax this a little bit. So maybe I'll just take the algorithm here. So the plan is just do this, but every once in a while, apply representation refinement, right? And then when you're saying find AI tilde and B tilde, when you apply representation refinement, you're applying it to the current substance, whatever it is, right? To the current vectors that you know, you'll change it. That's your view. So that's the argument. You don't have to do this every subspace. It's not to do it like every k. How can we hope to do this? This is a hard problem. So we'll relax this. Yes, I'll keep that there. And how can we relax this? Actually, it's nice if I write it next to it. I think the algorithm is simple enough that I don't need to keep going on that. Okay, so we want to relax this. How should I relax this? So the way we'll do it is, we'll say, we'll treat it as an optimization problem. Now at this point, this is not how the brain works as far as I know. Just this is a machine learning problem. Right? So I want to find a subspace. Right? I have a bunch of these points, A1 tilde, A2 tilde, so on. I want to ultimately find a subspace. Okay? So that the distances to each of these are small. It's small. All of them are small. This should be k-dimensional, let's say. Okay? So you want to find the k-dimensional subspace that minimizes the maximum distance. That's how it's phrased. So minimize, say t is a variable that represents the distance of, let me state it. I'm going to drop the tildes here because it doesn't really matter if it's tilde for the purpose of writing this down. AI transpose capital X, that's the variable, AI, less than equal to t. This should somehow represent the distance subspace, we'll see in a minute. X is going to represent the orthogonal space. So AI transpose X AI will be the square distance to this subspace. We're saying square distance at most. I'll make it very clear. X will be semi-definite. This will be the projection matrix times itself here. But how do we restrict the dimension? How should I restrict the dimension? That's the key. Like how do I restrict the dimension? Because if I don't restrict the dimension, this will just be the full space. And then the distance will be, this will be empty. And the distance will be 0. The orthogonal V will be the full space. And so I need to restrict dimension. So we'll say that the eigenvalues of X, first of all, so X itself is between 0 and identity. Sure. It's at most, we want to model a projection matrix, so the eigenvalues are 0 or 1, we'll say it's between 0 and 1. Still, this can give you a full space. The next thing we'll say is the trace of X So if it was actually a projection matrix, it would have only d minus k ones and k zeros, because it's projection to the orthogonal space. So we'll say the trace of x is equal to d minus k. So you really need to have total the sum of eigenvalues to be d minus k, and each eigenvalue is at most 1. That's the relaxation. So you can see here that if I have the true subspace V, I can choose a basis for the orthogonal space, which is d minus k dimensional. That basis times itself, it would times its transpose would be x, right? And so if yeah, and all the eigenvalues would be 1 or 0. So x would look like the summation of some ui transpose for I equals 1 to d minus k. That's your projection matrix. These are orthogonal unit vectors. So if I do ai transpose ai, this is just for any a transpose xa is summation of a transpose ui squared, which is exactly the distance in this subspace, right? The sum of the square distance. Each coordinate is orthogonal. These are the coordinate values squared. Great. Now that would be the case if your eigenvalues are exactly 1 or 0. But this is a relaxation. This we can solve in polynomial times. This is a symmetric program, right? And I'm actually quite fast now. But we're going to get back a matrix. It's not necessarily a projection matrix. You'll have eigenvalues between 0 and 1. So what we can do still is look at its singular eigenvalue decomposition, which will be some lambda I. Now you might have all d eigenvalues not 0, and some ui transpose. Right? These are unit vectors still. Let's say the lambdas are sorted lambda 1 in increasing order, lambda d. Okay, and of course they're all less than equal to 1. We know this. What should I do? How will you from this I have to extract a subspace? What would be your suggestion? The first k? Yeah, the first k would be for V, right? Take the span of the first k because they have the smallest eigenvalues, so you should get most of the distance in the other subspace. Okay. So yeah, so that's the plan. Now, what will that give us for an approximation factor? So yeah, so we're going to output span of u1 up to let's say k prime, but I'm giving myself a little room. Instead of stopping at k, I'll allow myself a little bit more. Okay. Okay. So the claim is that if I set, for example, k prime equal to 2k, then this square distance, right? T is at most twice opt. Opt is what you would get if you actually find the best k dimensional space, and this is at most twice. So basically, T is less than 2 epsilon squared, right? Because epsilon is the error in the game. Okay. I can write. Okay, why is that? So if I take any point A and I look at this, we already saw A transpose XA is in this case summation of I going from K prime plus 1 to D, right, of lambda I A transpose UI squared. Why K prime plus 1? Because the subspace X is only doing the from K prime plus 1 to D. The first K are in V, they are not in X. Right? This is the after rounding, this is what we're using. Meanwhile, the actual distance, because those are orthogonal vectors, and we're taking the span of these, the remaining parts, would be summation of AI transpose U. Oh, sorry, no, this will be, the relaxation gives you all 1 through D. Right? We can't control that. That's the distance measured by the relaxation. What we get is from k prime plus 1 to d of A transpose ui squared. This is what you'll actually get, because these are the vectors you're taking. That's the distance that you actually see. So the ratio is this divided by this. Right? So this is the sum over fewer terms, but the eigenvalues are all 1. This is sum over all d as given by the relaxation. Now, first thing, in this expression, these are all sorted. Ignore the first k prime. The remaining eigenvalues are at least lambda k prime plus 1. So this is at most 1 over lambda k prime plus 1. K prime plus 1. Simply because it's increasing order, so the smallest one. Okay, great. Now I want to say we want to put a lower bound on this so that this whole thing is bounded. How can I lower bound lambda k prime plus 1? We will say lambda k prime plus 1 must be at least how much? The sum of all the eigenvalues, the trace by the constraint, is d minus k. The sum of all but the first k prime is at most d minus k prime plus 1. I mean minus 1. Right? It's at most that. Yeah. Except the first k prime plus 1, everything else is equal because eigenvalue is at most 1, and that's the number of them. And so this is the sum of, this is the lower bound of the sum of the first k prime plus 1 eigenvalues. And the highest one of them is at least the average. This is the full trace minus what you're not using, because this is not including the first k prime plus 1 divided by the total. This is how much? K prime plus k prime minus k plus 1 divided by k prime plus 1. But now if I set k prime to be, say, some 2k or ck minus 1, then this will become c minus 1 over c, right? C minus 1 over c. So this is smaller than c over c minus 1. Okay, so if you use k prime equal to ck minus 1, you get c over c minus 1. In particular, if you use 2k, you get 2. You can get 1 plus epsilon, 1 over epsilon. So this is a tractable problem. You get an approximation. Fine. This is the change to the algorithm. I'll show you the algorithm is implementable and gives you an approximation. Now for the last piece, how do we actually, what can we say about the overall complexity here? For the theorem, this is with Sinuan Sao and Wei Yang Liu, and it's from this year. It's that the problem, so LLL RR with representation refinement solves this problem, is polytime and uses tilde d k to the 1.5 over epsilon plus m k over epsilon. Okay, so this term is fine. Remember, the previous result was d k squared over epsilon squared plus the same thing. And the optimal result we could hope for, if you don't have any time restrictions, dk over epsilon plus. Okay, so the epsilon dependence has become the correct one, but the k dependence is better, but it's 1.5. Okay, not quite. The proof I mean, something nice happens in the way the proof goes. It's not directly measuring the angular surface. I'll spend a couple of minutes on that. But I want to make one remark here. This might, regardless of how nice the proof is, it's still a bit unsatisfactory if we don't know the right answer. So luckily we can prove under in what one might call a black box setting a matching lower bound. So the theorem from the same paper, this paper is that suppose every time you learn one task, all you can say is that give me an answer to within whatever accuracy you choose, and the learner is allowed to give you any answer within that accuracy. That's what you would call a black box learner. With a black box learning algorithm for a single task, right? The sample complexity of any lifelong learning algorithm. So now it doesn't matter whether you use this algorithm, any refinement, do whatever you want, spend as much time as you want, doesn't matter. But for each task, you have to give it to a black box and say, give me to within error epsilon, it has to give you within error epsilon. Okay, you have to use. In this case, with the same A1 assumption, low concrete distributions, and so on, there is omega d k to the 1.5 over epsilon plus NP. So after the log factors that are inside this tilde, it's actually the right answer. So there is a price for efficient lifelong learning. If compared to the optimal sample complexity where you have as much time as you want and you get to see everything together. But any questions about this? Yeah. Oh, this is the assumption in the lower bound statement. So the problem is lifelong learning. But remember, the way we're doing lifelong learning is we're learning one task at a time. We have to learn. That's the goal. Every time you get a new task, you have to learn it. Right? And suppose when you're learning a new task to some accuracy, whenever you decide, I need to learn this fully, you ship it off to a black box and say, give me an answer to within error epsilon. Right? You don't have a control on how it is learned. It can give you any answer that is within epsilon. Then in that case, it is possible to set up tasks and a sequence of tasks. Actually, the task sequence of tasks M can be exponential in K, so that you can't do better than this complexity. So this is an assumption on how you learn one task when you learn a completely new one. Okay, so that's the thing. I should stop here.
We have time to take it.
Maybe I'll spend 5 minutes on how this proof goes because the idea is a little bit different. So rather than trying to directly bound the angle of the subspace, what we do is the following. We try to say that the set of possible candidate subspaces, given the constraints on it, are shrinking. Is shrinking. Okay. So if we let capital Y, the set of subspaces V, k-dimensional, such that the distance from every AI tilde that you've learned so far to V is less than some epsilon, right? If you look at this, or C epsilon, whatever, or make constant times epsilon. This is some set here, right? Say for all j going from 1 to I, and I'll call it yi. This is a sequence. Initially, this is a set of all subspaces, and then it keeps shrinking as you add more constraints. We want to say this is shrinking very rapidly. That seems hard to do because this set of subspaces is sort of a funny set. It could be in different places all over, So we will look at the same time at the set X of points in the unit ball. It's just the unit ball in k dimensions. Set of all unit vectors, right? Length less than 1, such that the distance from X to every subspace in yi is smaller than some target, some C prime times epsilon, where this is for all V in Y. So I'll call it yi here and xi. Okay, So this is a set of points that are close to all candidate subspaces. Now, this will be a shrinking set. Why? Because over time, we're only adding more constraints to subspaces. The set of subspaces is becoming smaller. The set of points closer to all of them will be increasing. But the nice thing about Xi, so maybe I will write the two key lemmas. So lemma 1 is that the Xi is a convex set, is a symmetric convex set. Lemma 2 is that it contains the true vectors, so plus or minus AI, this set convex hull is contained in Xi. Why? Because the true vectors are going to be close to all the candidate subspaces. That's the third is that the volume. So how should we measure the growth? I want to say that Xi is growing rapidly, but it could be a strange convex set. Those ones. So the volume of the large, let me call E of Xi, the largest volume ellipsoid contained in the set Xi. So the volume, that's how we measure progress. The largest volume ellipsoid contained in the set grows by a constant factor. We'll prove some constant 1.3, doesn't matter, anything with 1. So it's growing geometrically every step. Now the last thing we have to do is put bounds on the initial volume and the final volume. Okay. So the initial volume, x0, that's easy. Why? Because the point 0 is contained in all the subspaces, of course. And so 0 and a small ball around it will also be closed. So depending on what you choose to be your C prime, turns out we will choose C prime to be, we will choose the distance to be epsilon over root k, basically. It's an epsilon over k. So of course 0 is within epsilon over root k of any point of vector, any point that's length epsilon over root k is within epsilon root k of 0, which is in all subspaces. So the initial volume of this is at least the volume of the ball of radius epsilon over root k. That's the initial one, and it's doubling or whatever, going up by constant factor. The last piece is that the final volume, the maximum it will be, is going to be, we will stop, basically we will stop when the set Xi contains a ball of radius constant over root k. Why? Because now, if you scale this up by root k, your error will only go up by a factor of root k. And we're learning everything to the epsilon over root k. So scaling up by a factor of root k means your error is epsilon. But this entire ball of radius 1 over root k will be contained in Xi. That's the last step. And so this, if you compare these, you get you compare the volumes, and you're growing at this rate. That gives you the bound of k. The number of iterations is only k. You maintain the dimension at 2k or constant times k. But each time you have to learn to accuracy epsilon over. As a result, the complexity, which was, remember, it's d over epsilon times k. This becomes d k to the 1.5 over epsilon. That's the last. Okay, final remark. The sample complexity bounds also hold for nonlinear features with an additional factor of k. Maybe it will be too long to go into why, but we don't have efficient algorithms because even for one task, if it's nonlinear, there's no guarantee really in general. So if you assume there's a black box learner for one task at a time, then indeed you get the lifelong learning guarantee, d times k to the 2.5 is to 1.5 for epsilon. And there it's not clear if it's optimal. In practice, it turns out people use all kinds of heuristics in lifelong learning to refine presentation. And the students implemented this on various state-of-the-art test sets and compared them with seems to be a growing field, continual learning, or incremental learning, lifelong learning, and it actually outperformed these things on these 1,000-class data sets and so on. So there is some promise there, but of course there's a bunch of heuristics for the nonlinear setting, which I'm certainly not positioned to analyze algorithms, only the sample formats. So that's all I'm happy to answer, discuss anything.
So you're running this RR, where you're trying to find a new V tilde that's epsilon to the K tilde. Right? So won't those errors also add up each time?
Oh, no, we're not finding we're just finding a subspace. There's no longer any. It's just a subspace. Right?
But the constraint is that distance to A tilde should be at most epsilon.
The distance to it, yes, exactly, yes.
Right, but you might be running RR multiple times, so wouldn't the errors add up?
No, every time it's completely fresh. So every time we're making sure that the distances to all A tildes so far are less than epsilon.
So you're not finding a new A tilde in the new subspace? So
Sure, but given sure. So yes, so we are finding V so that the distance between V and A tilde I is smaller than epsilon. Every time. And the guarantee is that once you have this, you can use the same A tilde even if you want. You don't even need to change that because that A tilde already had error less than epsilon. You don't need to change those. But you will use this V to learn future tasks so that you get better error on that.
Doesn't matter how often you have to run it.
Actually, it turns out you can just run it once at the end. So the proof will tell you that. The advantage though is that if you keep running it once in a while, you keep the dimension at 2k. If you don't, the dimension will become something like k times log, because every iteration you could go up a bit more. Number of iterations it goes with the number of new complete features you learn.
if you don't do RR, can the dimension of this K tilde become really large?
No, so that's the thing. So this turns out that this part of this analysis applies even if you don't do RR to bound the number of iterations. But the dimension will grow with the number of iterations.
Right.
And the number of iterations is not order k, it's k log, no, it's just k log k over epsilon. So the dimension is a log factor higher than what it should be. So the representation environment is saving you a log factor in the dimension you're maintaining. Yeah. So I guess it's only logarithmically better to refine what you know.
Completely remove the log factor you have to run RR.
Doesn't happen. I mean, wait, in what? Log factor in the dimension?
Yeah.
Dimensions, right now we get that. So RR uses this, and I didn't write that part, and finds a subspace V, maintains a subspace V, whose dimension is order k. In fact, let's say less than 2k. You can make it any 1 plus epsilon. So it's always going to maintain within constant factor of the target. Yeah, because I mean this will work, but the point is that if k is higher than d, you might as well just learn every. Because suppose k cannot be higher than d, right? Because of course they're all already in a given. Yes. Yeah, that's d over epsilon is the basic dimension bound for general distributions, and it's also achieved for the distributions under this assumption. For a single one, no other. I mean, if you assume things like, oh, the half space has a margin, or the half space is sparse, depending on the structure that you assume, you can get better bounds. Right? Without any further assumptions, it's the best.
Can you hope to do something in case?
The algorithm doesn't. I mean, note here, the algorithm doesn't need to know k. Right? It's only in the refinement step. So if you don't want to do refinement, algorithms, I mean, you could also do it by say every time the number of features doubles, you can try to halve it and see if it works. But in terms of what you're doing, you're comparing with the span of what you already have and adding a new feature if you don't have enough error. So that doesn't need to know what the target energy is.
But the error to which you estimate that at k.
Right, but that you can use yeah. So basically, replace that k with the dimension of what you have so far. Right. So instead of epsilon over root k, use epsilon over root k prime.
So this you all know this with the assumption that you have a black box learning algorithm for a similar task. Is there any way if you remove this assumption you can actually break the heuristic?
Yeah, I mean, I don't know. It's a good question. I mean, certainly if you allow yourself exponential time, you can, because you will just, when you have k tasks, you'll just try to search for the best one joined. That's the next, find the best substance. But yeah, not clear whether it's possible to do it efficiently. Then it becomes a harder task, right? We really can't put lower bounds on computation time. This is the way to turn it into an oracle problem, and then you get lower bound. Yeah. The true sample complexity is decay. But then if you want to say it's decay, then you have to prove some kind of lower bound on time, which we only know how to do by restricting the algorithm.
Just tea downstairs.
Okay.
Some more t-shirt for you.
Yeah, I haven't instructed me to wear this one. So thank you.
So where is the tea within the non? Okay, tea downstairs in the same place.